Hi, my name is Golan Ben-Dor, and today I'll be talking to you about optimizing shared autonomous demand responsive transport, a case study of Jerusalem. This study is with Klein, Aleksey Ogulenko, Eitan Issa Zananiri, Eran, Ben-Elia, and Itzhak Benenson. My submission number is 39. So we used basically MatSim, which is Java-based open source multi-agent transport simulation. And it has inside four major stuff. So first you can do large scale simulation. You can have neighborhood, city, country. You have microscopic modeling of traffic. You can follow cars across links, public transport vehicles, the agents inside. You have the agent parts. So this is the behavioral modeling. So here's an example for an agent, which have home activity, work activity, lunch, and different desires, different modes. And in MatSim, you have co-evolutionary algorithm, which can modify this kind of activities to make them even better. So if an agent chooses to depart in a different time and it benefits him, it will do so in the next iteration, and also change route and change transport mode. So if an agent switched from car and went from bus to work and it benefits his daily utility, he will stick to that mode. So how does an agent obtain his score? Here you have an example for one agent. You have here the time of the day, and you have here the scores of different stuff. So you have here activities. So when you are at home or at work or at lunch, you gain positive value, you gain money, you're doing something. And on the other hand, if you are at driving or using a mode, you get a disutility, you get a negative score. So here with car, you get a bigger penalty compared to bus because you have insurance, you have gas, and so on. And the steep of car is much more lower because travel time compared to bus. This is not an optimal plan because the agent arrived quite earlier to work than the working time, so he gained a negative score. So this is the MatSim model for JAMA, Jerusalem metropolitan area. Here we have the center part of Israel in the northern part. This is the Jerusalem metropolitan area. This is this size. And we have here not a coarse network, which brings cars to the network, to the city center and Jerusalem area, which are external agents. So here we can see private cars, those green triangles. You can see different kind of travel times or congestion. And you can see here this blue dots are public transport vehicles with the capacity inside. So more blue colored means more agents inside public transport vehicle. The population is 500K agents. We have external agents and internal agents. The internal agents in Jerusalem is quite diverse. We have secular Jews, we have Arabs, we have ultra-Orthodox Jews, each one with different behaviors and different parameters. We have GTFS for public transport data. We have traffic counts. We have an ME network with 8,000 links. So the population we took from an activity-based model from the Jerusalem Planning Authority, and it was aggregated. So the activities of people were from traffic area zones to traffic area zones. MatSim is more detailed. You need to know buildings and the exact coordinates. So we have a shapefile of land use, GIS building, we matched. So if we saw agents inside a traffic area zone, which are going to a shopping, and we have a shopping building, we will assign them there. But we didn't only did that, we also assigned them based on the proportional size of the building inside traffic zones. So we will have more diverse distributions. So here is the output of what I just told you. So these dots represent activities and agents doing activities there. So it's in the night, everybody at home. And when I will start the video, you will see that if lights is red, it means that somebody went to work. And in the lower part, you will see the distribution across the day. So you can see at night, everybody at home, and the time goes by, the color changes, and everybody goes to work, school, and so on. So this is the distribution of the population I told you before. So in terms of calibrations, what we first did, we matched traffic counts, real traffic counts. We had 2 simulation volumes, and each dot here represents the number of total traffic cars per day. We also checked it across hours, but this is per day. And we can see without any calibration, the R square is quite high, close to 0.7. With calibrated, it's close to 0.8. How we calibrated, I'm not talking about it explicitly, but we modify the utilities of agent to prefer links with high traffic counts. And we also removed links from the periphery of traffic counts links for the calibration, and we got a higher results. We also matched the model to the model split. We have a travel survey. So we use as a basis the utilities of Berlin. They have an open scenario of Maxim, and then we just placed with the utilities until we got matching results. And the dynamics of public transport, we didn't need to do any calibration. You can see here Maxim data of public transport boardings and Ravkav, which are Israeli smart car data, and we didn't need to do any manipulations there. So now we'll be talking to you about the effects of congestion and parking prices in Jerusalem Center. This will be first without autonomous shared vehicles. So here we have the Jerusalem metropolitan area in purple, and we have here the Jerusalem city in green, and we have Jerusalem city center in red, and some attractions area such as malls and very industrial places. And we wanted to check different pricing schemes. So we checked congestion pricing once entering the red areas, and also parking pricing inside the red areas. So here we can see the car trips only for the city center polygon. So here we can see the total car trips to the city center is 67,000 car trips only. And we can see that without any fees, we have 69,000 car trips. And if we have €5 congestion pricing, it goes down, it goes even more when you increase the pricing. And we can see that €5 pricing of hourly parking price is similar to €10 of congestion pricing. The dwell time in Jerusalem Center is about 2.5 hours, so that's why it's similar. So what happens in terms of modal split? So here we can see modal split only for transport modes in the city center, not the whole metropolitan area. So 0 is the calibrated model I showed you before. And here we have different congestion charts, 5, 10, 20, and here we have parking prices of €5. So you can see with €5, it doesn't change much inside the city center. Some people move from public transport to cars, some move from cars to public transport, but when you increase to €10 or €5, the increase comes very high, and it takes from the car users, right? You can see here from 32% to 27% of car trips to the city center. And also congestion-wise, here is not congestion-wise and congestion pricing. So here you can see the city center, you can see the V/C. It's the volume divided by capacity on links. The values are from 0 to 1, and more red links, meaning more congestion links. So you can see the red is more red in 0, 1, and you can see in €20, you almost don't have red links. And this is also true in the southern part of the city. And here, if we can see the car trip to the center based on different congestion pricing, and also the V/C, the average V/C of all the links, which is here, we can see that the optimal charge is about €10, 30 shekels, something like that, more or less, probably more. So now I'll be talking to you about shared automated vehicles inside Maxim. So how does the algorithm work? So heuristic algorithm, very, very simple. So when an agent takes his phone out, he wants to ride a shared vehicle, he pressed the button, and then the operator checks if there's a vehicle which can arrive to the pickup point earlier than the maximal waiting time. If it has a seat open for you across all the day, and this is important, it checks that duration will not go over a certain threshold, which is TR max. What does that mean? TR direct is your travel time if it was a direct travel time, if you were driving with a private car. So if you're in a shared vehicle, you want it not to be 3 hours. So if your travel time direct is 10 minutes and the alpha is 1.5, the shared trip will not be exceeded of 15 minutes. And this is the first agent. What happens when you have more agents? So it checks that agent doesn't decrease its own travel time threshold, but it checks also it doesn't decrease to the other agents. And then the vehicle with the minimal average travel time for all passengers is chosen for service. This algorithm in the literature is very simple, very, very fast. And if no condition here are satisfies, you get a rejection. There's no service for you, and this is very important. We didn't check here the no rejection algorithm where everybody are served. So we extended the algorithm that an SAV can pick up passenger at public transport stop, not at home. They need to go to the public transport by walk to the stops and then inside a service area. We also made the algorithm twice as faster, and we made agents smarter because if there was a rejection in the original maxim, an agent just continue in the next iteration, try to certain stuff. But when the simulation is dynamic, kind of create a problem, right? Because today he got a vehicle, tomorrow he will not. So in case of rejection, we made an agent revert back to his previous plan before an SAV. And we also made SAV corridors. Instead of them roaming all the city, corridors to the city center and from out. We wanted to check what will happen with different pricing. I will talk about that. So we studied the effects of SAV service. So SAV price of the vehicle when you board it is the same as PT. We want it to be as a computation. Empty SAV, park at the end and wait for a new request. We checked 10 seats. We checked 250 and 100 vehicles. We checked a service of the full area of vehicle roaming everywhere for every kind of request, and also a core periphery service to the city center, the red. So if you have a request here, you can go to the city center only and out. So in terms of results, and this is results for the roaming, the whole area. So we have 250 SAV and 1,000 SAV with zero pricing. And the number of car trips, this is car trips only, because we want to see what the effects of congestion and car trips. You can see 66,000 K. So €5 lowers the price, and €10 also lowers the price, and parking prices are quite similar between €5 congestion and €10 congestion pricing. And if we check corridors that the SAV is going to the city center, where the people are getting the payment, there's almost no change from the results I showed you earlier. So here, if we checked the model split, right, between the calibrated model without any DRT, and we added SAVs, what will happen with different prices? So with €0, you can see we added 250 SAVs. We have 2% DRT, demand responsive transit, but most of it is from the public transport. We don't want it. So cars even got up because some traffic is freed. So we must use parking prices or congestion pricing to lower the public transport numbers. We want car users. And here we can see that 5 hourly parking prices, you get 5% less car trips to the city center. This is only model split for the city center. And here below, we can see how many agents change their behavior. So, right, so from the calibrated, here, this is the calibrated, how many change from car to car, right? So we have 2,000, and this is how many change, sorry, to shared automated vehicles. So you can see 4,000 move from public transport to shared automated vehicles. And when we have pricing, we have more car users going to shared automated vehicles. So I want to talk to you quickly about Jerusalem 2040. So in 2040, we have a massive light rail train and metro, which is the green here, I think. And also you can see that car vehicles are going to go up in numbers across the years, and also the number of buses, but the number of buses are not sufficient enough. And we ran a simulation for 2040 with the same utilities as 2020, and we get the same model split, although we have a lot more public transport vehicles and I think 2,000 more car links. So in this 2040 scenario, we have double the trips of car, of PT, and so on. And the car trips are almost doubled, and the speed is lowered by half. And the public transport speed is a bit higher because we have much more faster trains, because we have now only buses, then we will have trains, and so on. And this number of 55 minutes is with walking to the station, switching vehicle, and so on. And we checked it also inside the vehicles, it doesn't change. And we can see that boardings in the 2020 scenario, right? The boarding inside the vehicles, the number of passengers inside the public transport vehicles is much lower. So everybody's using the maximum threshold of public transport inside the 2040 simulation, and it's not enough. And if we check free parking in the city and hourly parking of 10 euros, you can see that the model split of the city center of the cars is much lower. We have increase in public transport, and also the average V over C in those links is much lower with 10 euros. And you can see we have much less congestion in this scenario with parking prices. So conclusions, given the 2020 conditions, 10 euros will reduce the congestion inside the city center. SAV facilitates access to Jerusalem Center for 2020 condition. Without any pricing, most users will move from SAV, from PT to SAV. And if the model and time utilities are the same in 2020, the model split in 2040 will remain similar, although more links and more LRT extensions. And we will have double congestion and double travel time. So we think and assume that pricing can be the only solution also for tackling with congestion. You must give users different possibilities. If you just throw shared automated vehicles, it will not solve anything. If you just throw new public transport line, it will not solve anything. You must have a carrot and a stick for the agent to induce them to move to other modes and make life better for everybody. So thank you. And if you have any questions, you can just contact me in private.